All right, and as we told you, this is going to be the 3-2 beta lesson. We're starting here, Stat Calc 8. Now, get your calculator. You just need to be aware of something. You go to your calculator and you go to Stat Calc. You're used to using 4 for linear regression, okay? Where A is essentially M, the slope, mx plus b. In statistics, we use 8. Now, it doesn't matter. What happens is these values for A and B just exchange. These values are just written alphabetically. First letter to come up, A, then B. So the way you're used to doing it is the slope times x plus the intercept. And statistically, it's written with the intercept first and then the slope of x. And the reason is because you get into advanced statistics, you're going to deal with multivariable statistics, which is the way, things are analyzed. There's more than one explanatory variable in most scenarios. So you just get used to using Stat Calc 8 instead of Stat Calc 4. Ready? This line's important. The 2 lines underneath it are not a big deal. What is this saying? For the line of best fit, this is the slide you're doing. So if I just make up this problem, see if this is still in here. It is, okay. So I make up this problem where the grand mean is here, 2 to the right and up 3. What does that mean? Of all the data points, I just took something that's user-friendly. Of all the data points, you have the scatter plot. The mean of the explanatory values is 2, and the mean of the response values is 3. So when you do regression, what the calculator does is draws this vertical line through there. A horizontal line through there. Looks like that. And then it'll rotate the line in order to minimize the sum of the squared residuals. So here, this is saying we know what the slope is. It's b sub 1. Now we're going to do this transformation to drag the line through the grand mean. You did this transformation in Algebra 2. You did it in pre-calc. You're doing the opposite. So we calculate the slope. Here's how it's done. You're not going to have to do this by hand. You calculate the slope in the line of best fit. So we go back here and say the slope was 1. Just to make this user-friendly. If the slope's 1, it looks like that. But it doesn't go through the grand mean. So we're going to pick it up and drag the origin 2 to the right and up 3. So that it will go through the grand mean. In order to do that, we go to y equals. If we're going to go 2 to the right, we replace x with x subtract 2. We're going to go up 3, replace y with y subtract 3, and to make it calculator friendly, you add 3 to both sides, and now the line of best fit goes to the grand mean. So this exercise right here, which is just a transformation, a translation, is what's going on here. And then we're just solving y by itself. This is not something you have to concern yourself about. The intercept, statistically, is referred to as b sub 0. And the slope is referred to as b sub 1. So this is just more symbols that you're accountable for. For example, down here you have y hat. You need to know what y hat is. Okay, y hat is what you get. It's after you do the regression. It's a predictor line. So if you see a hat over the y, you're trying to predict something based on a line of best fit. B sub 1 stands for the slope. B sub 0 is the intercept. Okay? Where's the slope coming from? Well, you've never done this before. You just ran things in your calculator. So the slope is coming from this. The sum of the product. The sum, sigma for sum, of the product of how far each x is from the mean times how far each y value, how far each height is from the average height. All of that divided by the sum of this first term squared. That's where your calculator is getting the slope. When you put all those terms in there and you do linear regression, that's doing that for you instantaneously. Okay? Is a linear model appropriate? So if a linear model is the best model, and what we did in pre-calc is we compared the R values. Well, we're going past that now. If you look at the residuals, if a linear model is appropriate, you will have a random scattering of residuals. There will be no pattern to the residual plot, whether that's plotted against the x-axis or plotted against the line of best fit. If a linear model is the most appropriate model, and you'll see that when we get to the problems, there will be no pattern. Okay? This is something new. So you need your calculator for this because you want to be able to find this. Two terms, one you're familiar with, one you're not. S. You ever seen this before? It's the standard deviation of the residuals. Now think about this. It's just the residuals, how far the heights are from the predicted height. So if you're above the line of best fit, you have a positive residual. That was from yesterday, the alpha lesson. If you're below the line of best fit, you have a negative residual. So now what do? You find the standard deviations of those. How far they are from the center. We're squaring them so the negatives don't work against the positives. We're going to take the square root. After you divide by n, take away 1. Now, on your calculator, when you do linear regression, go here now together so you see this. When you do linear regression, the value will come up here. I'm not going to get anything. Well, whatever was last in there. You go to vars, which you go to a lot here for second distribution A, just without putting a second key, and type 5. When you type 5, well, it's pretty, transparent statistics. You have these drop-down menus. You got 5 drop-down menus. And every time you do regression, these values get loaded up. And then they get written over. They stay there till you do something. You do something else. This is the only place to find the standard deviation of the y values. It's here. The test drop-down menu at 0. You can't find it in the catalog. Now, I don't know how often you have to find it, but the point is if you do linear regression and most of the time you'd be given a value for S and then asked to interpret it. That's more important. But here's where you find it. Every time you do linear regression, a new value gets pasted there until you do it again. So on the PDF, you can come back here and it's showing you where it is. I'm giving you the screenshot of stat, of distribution, vars 5, go across the test, but you have to drop down to C0. Now, R squared, we showed you that yesterday when you have the diagnostic turned on, the calculator will spit out R squared, which is literally just the R value multiplied by itself. But this is important that you know the definition of R squared, or the meaning in terms of the significance of statistics. It is the proportion of change in the output, in the response variable that can be attributed to the change in the input, which is the explanatory variable. This is not negotiable. You need to memorize this. There are a select number of things, probably a half dozen things that you have to memorize here. It's not complicated. Right? I memorized a rap for the honors reception video. And the rap was the chain ruling, implicit differentiating, sample bias identifying, R squaring, Z scoring, P valuing, F2Ring, sample bias identifying, goal achieving, SHS AP math students. So if I can memorize that, you can memorize R squared. Okay. So we're going to go to two problems. 47 and 51. They're two separate data sets. And 47 is on page 204. All right, so we're going to pause this, give you a chance to do those two questions and come back to it. All right, so we're going to go over these two questions, then we're going to actually go forward to the other question also. 47, ready? You get this. Now, instead of them saying Y hat, they say weight hat, because they're doing this in context of what the data is. And in this data, the weight depends upon the age, okay? The weight of infants. So you have this regression equation. Here are the residuals. What does that mean? This data point, this child had a negative residual below the mean. Negative residual below the line of best fit. Those two are below the line of best fit. Ready? Pretty much on it, above, above, above. This, a linear equation, is not an appropriate model by just looking at the residuals, because there's a pattern to it. And if there's a pattern to the residuals, that's telling you that a curved model is better than a linear model. In order for a linear model to be appropriate, this thing would have to be randomly scattered. Below, above, below, below, above, below, above, above, something without a pattern. 51, you had to put the data in, the list. And what happened in 51? The calories depended upon the sugar. All right, so we actually have a couple of movie theater employees here, and this is the poison that they're selling at the movie theater, and it tells you how the calories depend upon the sugar in these candies. So what happened is we just put this in a list. I went to second y equals and drew this scatter plot. But if I'm going to describe this, I would describe this as linear, positive, weak. Now, if you say linear, positive, moderate, I'm not going to argue with you. Okay? And then I didn't show you the window, but what did I do? I went to the lowest amount of sugar, which is 44, and I made the X min 40. I just stretched it from the min and max of the two lists. So we get this, okay? Now, when you do linear regression, you can store it in a y equals, and it'll draw the line and superimpose the line on there for you, which I didn't do here. I just went to linear. Oh, I did do down here. So here it comes. So I went to linear regression. I'm telling you what I did. List 1 and list 2. List 1 is the input, which was sugar, the explanatory variable. Calories are the response variable. And I put it in Y1. Here was your option to do that. Store the regression equation. So it superimposed the line of best fit on the scatter plot. Here are the equations. Or here's the line of best fit. Ready? 300 is the intercept, which means what? If something had 0 grams of sugar, you would expect it to have 300 calories, but that's extrapolation. Okay? Now, this is saying to you, it's called the least square regression line because if we take a residual, take this one, and we drop down a perpendicular, you literally box it off, you square it, and you would have all these shapes, these squares on here, and this blue line is the one that minimizes the sum of the squared residuals. If we were to add these residuals, we'd get a 0. The values above the line, the positive residuals, would add to the negative residuals to give you a 0. So we square it, but it geometrically means to draw a square. And the line of best fit would have the sum of the squared residuals would be minimized. Now what? You see in the output, you don't get S. You don't get the standard deviation of the Y values. You do get R squared. So my interpretation of this problem is 38% of the change in the calories can be attributed to the change in the sugar. That's a big deal. Interpreting R squared. And then you didn't do this problem, 55. 55, they give you S, and they give you R squared, and they ask you to answer them. So here's the standard deviation of the Y's. There's the algorithm. Now this is new. Don't worry about it. You're divided by n, take away 2. Well, first off, I want to divide by n because I want the average, yes. And now you're telling me the last month divide by n, take away 1. Because I only have the sample, and now in linear regression, I divide by n, take away 2. Yeah, it's confusing. You're not going to have to do this until we get the linear regression in the spring. So that's the algorithm. But what does it mean? They're telling you it's 3.5. The typical residual is 3.5 steps, 3.5 units, whatever this is, in case, from the predicted value. And R squared is this. About 40% of the change in the input can be attributed to change in the output. Okay? So